All right, welcome to the next round of lectures. So this one's going to be about two kind of very different things. So we're going to get down and dirty with bits, and then we're going to talk at a very high level about how to manage projects as you program them. So it'll be very interesting. Okay, so I guess let's just get on into it with the very low level stuff. So bitwise operators. So bitwise means it's working on binary numbers, on the bits of a binary number. So it would be nice to remember what a binary number looks like, right? So we've talked about ones and zeros. We know how to translate, the number 7 in base 10. We know how to figure out that that is going to be 4 plus 0 plus 1. No, 4 plus 1 plus 1. There we go. Base 2. It's hard to do it in your head sometimes. So this is the 4's place, this is the 2's place, this is the 1's place, and you add them all together, you get 7. So that is your 7 in base 2. Okay? And you can put as many zeros as you want to that on the left side of the 7. Okay? So sometimes you have 8-bit numbers, and if you want to store 7, well, you have to put 5 zeros over here if you want to make it an 8-bit number. Okay? You can pad with zeros on the left all day long. And the number doesn't change. And so remember, the way to go back, so if you had a binary number like 101 like that, to go back, to convert that to something in base 10, remember the algorithm that it's just following the process of doing those powers exponentiated. So we have, on the right, we have 1 times 2 to the 0, and that's this digit. And then to get this one, it's 1 times 2 to the 1. Oops. There we go. And then this one is 0 times 2 to the 2, 0 times 2 to the 3, and then 1 times 2 to the 4. And so that's how you can do that. And eventually you can translate this back. If you do math in base 10, you can translate this back to 2, 4, 8, 16. 16 plus 2 plus 1 equals 19. Okay? Because this was the 1's place, the 2's place, 4's place, 8's place, and the 16's place. So 16 plus 2 plus 1 is 19. And so that is the way that we represent numbers in a computer. We've got zeros and ones as far as the eye can see. Okay? So I think that's everything that I wanted to say there. We have been talking about primarily positive numbers. 0 is just a bunch of zeros. And we've been talking about nothing but positive numbers. But the idea is we have the int type, and it holds negative numbers. Okay, so int holds negative numbers, though. How does it do it? In particular, remember how big an int is. It's 32 bits long. And some of those have to get prioritized for negative numbers. Some of those numbers that you can make with 32 bits have to be positive numbers. Okay, they're not all positive. So let's talk now about storing negative numbers. Okay, so what in the world should -1 be? And I know a good way of figuring out what it should be. I think if you think long enough, you'll come up with the same idea. Well, it should be whatever -1 in binary is, in 32 bits is. adding it to 1 should make 0. You see that? That's how we can figure out what -1 should be, and then we'll try and figure out if we find a pattern. Okay, so let's do this. Let's pretend we have 8-bit numbers. Okay, so assume 8-bit numbers, and we need to figure out what -1 in base 2 is. Okay, sorry, -1 in decimal is what in the world in base 2 8 bits. Okay, so that's what we need to go and figure out. And the idea is, if we add this secret thing to 1, it should make 0. So we've got, here's 1, it's 0, 0, 0, 0, 0, 0, 0, 1, yeah? And then we need to add this to something, and we need to get back 0. We need to get back a bunch of zeros. 0, 0, 0, 0, 0, 0, 0, 0. What in the world are we going to do here? So we're actually going to take advantage of the fact that if you carry far enough, like you carry way over here, it just gets discarded. Because there's not enough room, there's not a 9th bit, okay? So just like for 32-bit numbers, there's not a 33rd bit. This all can be extrapolated. So the idea is, well, this is going to be a 1 if we don't put something here that is not 0. Okay, because so if I put a 0 here, this is guaranteed to be a 1. We can't do that. What are we going to do? Well, we have to put a 1 there. Okay, so we know that the last bit of -1 better be a 1. You see that? All right, so that'll make this a 0. This will carry, and be 1, 0. And now what in the world are we going to put here to make sure that this one is also a 0? Because right now, if we put a 0 here, it's going to stay 0. Or sorry, if we put a 0 here, this 1's going to get put right there. We don't like that. We better put a 1 here. Ooh, I think you see the pattern. So again, like that's going to now carry, because 1 plus 1 is 1, 0. In binary, it's 2. So this is going to get carried. If we want this to be a 0, we have to start putting another 1 here. And so you can play this game all day long, and eventually you will notice that -1 in binary, in an 8-bit number, in 32-bit numbers it's just a bunch more 1s, it has to be all 1s, okay? Because you want all these to carry. 1 plus 1 is 1, 0, 1 plus 1 is 1, 0, 1 plus 1 is 1, 0, carry the 1, 1, 0, there we go, another 1, 0, 1, 0, 1, 0. So 1 plus 1 at the very end is 1, 0, but we don't do anything with the carry. So we're carrying a 1, but we're carrying it to nowhere. Okay? Just vanishes into the ether, and then suddenly we have 0. Okay? So it has to be all 1s. So A1 in binary is all 1s. We take advantage of the fact that the last bit, like the last carry operation, just gets disappeared. Okay? So that is -1, and the pattern is hard to see. If you do this with 2, 3, eventually you'll get it, but the whole purpose of school is to speed up your lives, so let me give you the idea. So the way that we store negative numbers in a computer these days is called 2's complement. And the steps that you take to generate a 2's complement number, to negate a number. First, you flip all of the bits. And then you add 1. Okay? That's all you need to do. To negate a number, flip all the bits, and then add 1. That is how you get this 2's complement form, which is the way that we represent negative numbers. So if you do this to 1, it'll make it -1, okay? So let me give you some examples. Let's do it for 1. Let's prove it that it's going to work. So first we started with 1. So we're going to flip all the bits. So this becomes a 0, and all these become 1s. And then we add 1. And then it all becomes, that becomes 1, 1, 1, 1, 1, 1, 1, 1 finally. And if we did the same with 2, this would be -2. I guess I'll just do it over here. Originally, +2 is 0, 0, 0, 0, 0, 0, 1, 0. Still 8-bit numbers. This all transfers to 32-bit numbers, or of any size. Numbers of any size at all. So we're going to negate this number. We're going to convert it to 2's complement form by flipping all the bits. 1, 1, 1, 1. And then do it some more. 1, 1, 0, 1. And then we add 1, which turns this part into 1, 0, because this one gets carried, and that's the end of that. So +1 is now 1, 1, 1, 1, 1, 1, 1, 0. And if you add this to this, you will get 0, and you know why, because all these will carry for the rest of time. Okay? That's the idea. Okay, that's how you store negative numbers. And so now you have a better idea of like how we're actually like representing numbers inside of our computers. We found a special way to store them in a fixed number of bits that lets us do cool things with them. Okay, so now let me switch gears a little bit. We've been using numbers to store numbers, but that is not always necessary. Inside of ints, you might want to store 32 Boolean variables. And save a whole lot of space that way. So the way that you do that is you can individually do stuff with individual bits of a number. So there are ways to do things with individual bits of a number. For example, like get the 12th bit, set the 3rd bit to a 1, etc. Flip them. So one of these ways that you can access individual bits and do stuff to them is with what's known as the bitwise AND operation. Lets you perform the Boolean AND operation on each bit of a number. So again, let's assume 8-bit numbers, and let me show you what the AND operation does. So remember your normal truth table, just like with true and false, the AND operation, like Boolean AND. Let's remember that. If you have, let's see, how do I want to do this? If you have, I think I want to do it this way. Let's see. If you have P and Q, and then you wanted to know what P and Q is, if these were Boolean variables, I'm going to show you how these all line up in just a second. P is true, Q is true, or P is true. Q is false, or P is false, Q is true, or they're both false. You know that if P holds true and Q holds true, the AND of them holds true, and then false otherwise. But also remember that each digit of a number, like you can imagine, is true or false. Each bit, like 1 is true, 0 is false. For as far as this operator that I'm about to show you is concerned, bitwise AND looks like this. if you didn't think the ampersand was overloaded enough, there is a third thing you can do with it, and that is bitwise AND. So let me show you the idea. Let me just make some random 8-bit numbers. And then you can bitwise AND these with an ampersand, a single ampersand. And what it will do is it performs the AND operation, the Boolean AND operation on the individual bits of a number. They just line up like that, okay? So it ANDs them together. Okay, so it just does them in order. So it first considers these two. What's the AND of them? Well, true and true. That's true. So it's going to make a 1 out of this. And you'll get back a number after this. So just remember that this is not address of, not reference. It is the ampersand operator being used for a third thing, I guess. Which is so silly. And then it'll go and consider these next 2 bits. It'll be like, okay, false and false is still false. True and false is false. Oh gosh, I wrote this in a horrible way, didn't I? This is true and false is false. False and false is false. True and true is true. False and true is false. True and true is true. So this is the final number you get back after the AND operation, the bitwise AND operation. This is your final answer. Okay, you can AND together 2 numbers and it'll just perform the AND operation on those individual bits. Okay, so that's the idea, and I think you can kind of see what it's good for. It's good to like extract bits. Like the second thing that you give is like what gets extracted if it's a 1. Okay. You just give 1s in your second number where you want to extract the bits. Like I want to extract these first 3 bits here, and so if they're 1s, I will get them. If they're 0s, they'll become 0s still. And if I don't want this bit, I don't care about it. I don't care about any of these. I'm going to make it a 0. That makes it always a 0 as the final answer. Okay, I hope that makes sense. Are good for this AND is good for bit extraction, and I will show you that in an example. So let us go to the good old VirtualBox, and let me make a program called Bitwise. Let's just do them all in one. Bitwise ops.cpp. And let's see here. We will do, let me make 2 numbers. What should they be? Let's make it be 1, 1, 1, 1. What's that? That's 15, right? And 0's forever. That's equivalent to 15, because it's 8 plus 4 plus 2 plus 1, which is 15. All right, so let's make int x equals 15. And then let's extract the third bit from 15. Okay, so let's figure out what the third bit of 15 is going to be. Okay, so the third bit is, well, I'm going to consider this the 0th bit, so this is the 1, 2, third bit right there. So let's go and get that one. So how do we get it? Well, we can extract it and see if it's set by ANDing with a bunch of 0s and a 1 right there and a bunch of 0s. You see that? I can figure out if this one is set by ANDing with this. And if it is set, I will get back a 1 in this position, and 0s elsewhere. If it's not set, I'll get back a 0 here and 0s everywhere, which means that the final number would be 0 if it's not set. Okay, so potentially I'll get a 1. I'll definitely get a 1 in this case. Alright, so let me show you how to do that. So this is 1, 2, 4, 8. So I'm going to and with 8. Okay? We're going to and with 8. So cout x and 8. I'm not actually sure if I need to put these in parentheses. We'll find out. And so the idea is, yeah, I definitely do. The idea is, this is either going to be, if it's set, 0 or 8. Okay? Dun dun dun. So let's go ahead and compile this. Actually, let's use a makefile. Why not? So how in the world are we going to make it bitwise ops.cpp? So I want it to be called the final program, bitwise ops. And it requires bitwise ops. Let's go through a .o file first. How do we use the .o file to actually compile the thing? Well, we can say g++ standard equals c++ 17 bitwise ops.o -o bitwise ops. Beautiful. And how in the world do we compile bitwise ops.o? Well, that requires bitwise ops.cpp. That needs to exist first. Check if it's changed. And then we'll say g++ -c bitwise ops.cpp. That's all. Alright, so now it'll go through the .o file, make it first, because it requires it, and then it will link it with the standard library and other things to finally compile. Beautiful. So now I can say make bitwise ops. Alternatively, I could just say make, because the first rule is the one I want. And bam, it goes and compiles it. I now have the .o file and the executable, and I get 8 back. So the idea is 8 is 1, 0, 0, 0. The zero's over here as well. In binary. And so it will extract that third bit. Which is super nice. If that bit wasn't set, notice that if I have a 0 anywhere in a number, it's automatically never going to be anything other than false, because one side was false. That's what AND does. It only is true if they're both true. So the number, if that bit wasn't set, the result would be 0. I hope you see that. So let's use a number that doesn't have a 1 there. Let's find the number, let's see, 1, 0, 0, or 1, 1, 1, like that. So it doesn't have that third bit set, but it has the one after it set, for example. Okay? That's the difference. So this is the, it's going to be 1 plus 1 plus 1, or sorry, 4 plus 2 plus 1, which is 7, plus not 16, but 32, equals 39, doesn't have the third bit set. So if I'm going to do cout 39 and ended with 8, this will actually print out 0, because that bit is not set. Make 0, okay? That's the idea. So that's how you can tell. You can tell if a certain bit is set, whether or not it gives a non-zero number back to you. Okay, so to figure out if a bit was set, check if the AND operation gave back a non-zero number. And I think you know a few ways to do that now. Okay, so that's the AND operation, bitwise AND, and the rest are going to go very fast now because you know the game. So bitwise OR just does OR on the on those bits. So logical OR was 2 little pipes. Bitwise OR is just 1. The bitwise OR operator is just a single pipe, it ORs together every bit in a number, just row by row, okay? Or column by column. So again, if I had, let me pick some other numbers. If I had 1 0 1 1 0 1 1 1, actually, and that's fine. And then 0 0 0 0 1 1 1 0. How about that? So if I OR those with just a pipe character, it's going to OR together each individual bit, and so true or false is true. So anything that's not double zeros is going to be true, right? So true or true, yeah, one of them was true. At least one of them was true. 1 1 0 1. So remember that OR gives back true, and at least one is true. Alright, so that's the result of the OR operation, and so you can see that the one of the nice things that OR does is it can set bits. This next thing, you can make sure that it's going to set certain bits. Like this one, if you put a 1 here, it's guaranteed to be 1 in the output, regardless of whether or not the first one was a 1. You see that? So just like AND is good for checking bits, OR is good for setting bits. Like maybe bit 3 was like, I don't know, game over. And now it's true because you lost the game, so we're going to set that bit. Okay, that's the idea. Because when you OR by something, it's always going to be true. Just put a 1 in that bit location. So build up a number with 1s in the spot that you want to set. Okay, like I want to set those things. So, for example, sets bits 1 through 3. Okay, because these are 1s, they're guaranteed to always be 1, regardless of what the original thing was. Sometimes it's not a 1 yet. Okay, so that is bitwise OR. So let me, I don't know, starting from 0, let's make 15 maybe. I don't know. So let's set bits 0, 1, 2, and 3, starting from 0. So see out, well, start with 0, or with 1, or with 2, or with 4, or with 8. You see that? That's the idea. So do this one first. Let me put them in extra parentheses. Do that one first, then this one over here, then do the 4 as well, and then do the 8. Okay, so that's the order of the ORs. First we do this OR, get a final answer, then we're going to OR with our 2. And remember that these are just all single bit numbers. There's only 1 bit set in all of them. So 1 has just a single bit set, 2 has just a single bit set, 4 has a single bit set, and 8 has a single bit set. This is the 3rd bit, this is the 2nd bit, this is the 1st bit, this is the 0th bit. Alright, so this should print out, oops, if I actually close the line, this should print out 15. Okay, because we set all those bits individually. That's the idea. We can go and check them now too with our OR, or with our AND operation. Okay, bitwise not now is going to be nice because that's just, oh sorry, I already had that one. I had it twice accidentally, sorry. So bitwise not is also sometimes called complement, and here is what it does. It just flips all the bits. And your Boolean logical not was an exclamation point. It's not like 2 exclamation points or anything like that. It's actually the operator is the tilde. It's like flip all the bits. Alright, so if we had, for example, 1, 0, 1, 1, 0, 0, 1, 1, and we knotted that, we'd get back, well, just flip all the bits, 0, 1, 0, 0, 1, 1, 0, 0, and that's that. Okay, so that's the complement of a number, just flip all the bits. So, for example, a good example is, hey, let's negate a number by using 2's complement. You flip all the bits and add 1, right? We know how to do that. So, see out. All right. Start with 1. Flip all the bits. Negate 1. And then add 1 to it. So this should build up a binary number that represents -1, and it'll print out -1 to us. Okay? Unless it does a certain thing, and I'll fix it if it does. Yeah, so it does give us back -1. Perfect. Awesome. So I'm very happy about that. All right. The next one is a weird one. It's called XOR, which stands for exclusive OR. That's the idea. And what it does is, well, let's talk about OR for a second. Remember how OR is true if any of them are true? Doesn't matter which. Exclusive OR is a little bit different. It takes the other approach, like normal OR. It gives back true when either is true, or 2 elements are true. Okay, when 1 or 2 sides are true. So either one goes. It's what's known as, technically it's called inclusive OR, if you want to be pedantic. So it's like everybody gets a say in whether or not this is true. It doesn't matter. I will include the case when both sides are true as well. Exclusive OR is the opposite. It is true only if one of the sides is true. So here is the XOR table. So if we had, I don't know, P and Q again, let's see if I can copy this first table actually, that would help. Well, let's erase some stuff. Whee. So P XOR Q, if we did the mathematical operation on the actual Boolean variables, it would look like this. So it's true if only one is true, but not both. Okay, so this one's true, but that one's false. That one's false, but that one's true. So those are the 2 cases where it's true. The other 2, this one's false as usual, but this one is also false up here because they can't both be true in an exclusive OR. Okay, only one can make it true. Okay, that's the idea. So exclusive OR just does, the bitwise XOR does this on individual bits. Okay. The bitwise XOR operator is the caret. And this is why starting programmers get messed up sometimes. They think that this is to the power of. And I think maybe a long time ago I told you that, oh no, that is not what that is. And this is why. Okay, so. Okay, it was all along the exclusive OR operator. So, I don't know, let's give some numbers. 0, 1, 1, 0, 1, 1, 0, 1. And if we exclusive OR these 2, we are going to give true back in the final answer if they're both, or if only one side is true. Okay, it doesn't matter which. So this one's true because this one's true, but that one's false. exclusive OR. This one's true, this one's false, because they're both true. Can't have that. This one's true, true, false, true, true. Okay, that's exclusive OR. And you won't believe me right now, but once you take CSCI 45 one day, this is why I'm teaching it, eventually you're going to need this, it's kind of like addition. XOR is kind of like addition. And I'll leave you there. It is, in fact, one bit addition. If you do XOR, like 0 XOR 0, oh, that's 0. 0 XOR 1, oh, that's 1. 1 XOR 0, oh, that's 1. 1 XOR 1, oh yeah, that we have to carry anyway. That's 0. Ooh, this is interesting now. So it really is addition. It's doing addition in a sense. And deep inside your computer, it's actually doing a bunch of XORs with some extra move the carry around kind of stuff that you will learn about in CSCI 45 if you take that. Okay, that is all I wanted to say for XOR. So yeah, just use the caret operator. I don't think I need to give it a good example of that. And finally, the last bitwise operators that I want to show you are the shift operators. Okay, so this is what they look like. You've actually used them before. As a matter of fact, they've been overloaded. So the bitwise shift operators are left and right shift. Okay. So they don't take well, they do take two numbers, but the second number doesn't do what it has been doing. Okay. So what they do is they shift to the right or to the left. Left shift makes more sense, so let's talk about that. Left shift, like shifts all the bits in a number to the left, adding zeros. Okay? So for example, if I have, I don't know, the binary number 000, 0100, like that, which is 1, 2, 4. It's in fact 4 in base 10. If I left shift that by 1, you put here the number that you want to shift by, you get back a number with this, all these bits shifted to the left by 1, so adding a 0. So it's as if we added 1 here and got rid of that one. That's the idea. So what it does is, okay, now it's 100. We took those, shifted them left, and we added another 0 here. Okay, we brought in a new 0. And then we have, I guess that's where the 1 goes now, and we have zeros around here still too. So this one actually goes away. The last bit goes away. But this is the idea. And so we made 1, 2, 4, 8 out of that. Ooh, this is interesting because of the fact that we're using base 2. One good thing that bitwise shifting is good for is, well, it's another way to multiply by 2. Multiply by powers of 2. So if you shift left by 1, you've multiplied by 2. Shift left by 2, you've multiplied by 4, for example, and so on and so forth, which is super nice. And so now, like, if you want to set the third bit, like if you want to get the third bit, in a more easy to read way, you can say, all right, I want to take x to get the third bit, so I'm going to AND it with 1 shifted left by 3. You see that? So it's going to shift 1, which is, I'll just write here, 1 is just 1, and then we're going to add some zeros to the end of that. 1, 2, 3, 3 zeros, because we're shifting left 3 times. Now suddenly, I got this in the right position. Now it's 8. You see that? Yay. So, that's a lot cleaner, and most programmers use this. Instead of like thinking what number should this possibly be, they just use the shift operator. And so we'll get back 8 again. Beautiful. And then right shift, that one's a bit more interesting. Right shift shifts the bits to the right, yes. But it does it in a fancy way. Because we might have negative numbers. Right shift on ints brings in either a 0 or a 1. 0 if it's positive, 1 if it's negative. And then right shift on unsigned ints, because we're not using negative numbers anymore, brings in a 0. So on unsigned ints, it makes a lot more sense, or on positive numbers, it makes more sense. It divides by powers of 2. Okay, so if I had, again, my 8, and I shifted that right by 1, or let's do it by 2, that would become, well, boop, boop, that goes away, add some zeros over here. It's going to be 1, 0, which is just 2 now. So 8 divided by 2 to the power of 2, which is just going to be 2 now. Okay? So that is shifting in a nutshell. So I've gone and confirmed that this is usually the case, but it actually is only the case on, this one is the case for most processors. It doesn't have to always be the case though. Okay, so normally, like in your lab, I'm going to be giving you unsigned ints just to make sure that this problem doesn't happen. Okay, so that is the idea there, and yeah, I think you are now an expert in bitwise operators. And I don't want to start a brand new thing right now, so I will end this current lecture, and then I'll come back and talk about software development, software engineering. So I will see you in the next lecture.